Calorimetry is the process of measuring changes of energy. This is also known as enthalpy, and it depends on the mass temperature changes. So we use this formula here, Q is equal to mCT, and using that, calorimeters, you measure this energy change thanks to that formula, and then we, let's say, produce heat. Okay, so let's say it's an exothermic reaction. So this heat that's released must be kept contained and not lost to the environment. If it does, it's probably a small amount, it's negligible, so it's not a big deal. If we use a dilute solution as the one that is absorbing that energy that got released from that substance, right, from that system, we just assume that it has the same density and specific heat capacity as liquid water, just to make calculations simpler. Well, let's look at this question here. Peroxide, as you can see, is the system, right? So it's the substance that is releasing energy, but we care about water that is taking in that energy that got released from the peroxide. So how much did the water temperature increase? Well, let's just use Q is equal to mCT because it has the delta T variable here, so we got to use that one. So as you can see, I have substituted all of the values for water, okay, because we care about the water. But Q, what is it? Well, where is Q in this thermochem equation? We see a negative 285 kilojoules. However, this is negative 285 kilojoules for 2 moles of Na2O2. So if I just divide all of these by 2, I can get a different molar enthalpy value. I've done that over here. So I have, as you can see here, negative 142,500 joules per mole of the Na2O2. However, I cannot add this over here because that doesn't make sense. This is Na2O2 and this is all about water, so it doesn't work. So I have to change this into my water. So I've already done my molar ratio and then the conversion from grams to moles, and I've found my moles of H2O. So if I were to bring this down here, now I have 0.10003 moles of H2O. This mole cancels out, so I just do this times this. I end up getting 14,253 joules of H2O. So again, I want to isolate my delta T, so I just divide these by itself. If I do it on the right side, I need to do it on the left side, so I get 30.9 degrees Celsius approximately. Again, I didn't put this as a negative because it has to be positive because it's the water, right? It's taken in that energy that got released, and it's taking it in, so it's endothermic, so it's going to obviously increase in temperature, so it increased by this temperature. In bomb calorimetry, however, both the medium, right, so our H2O in the liquid in the state, and the bomb calorimeter need to be taken into account. So by doing that, you just use Q is equal to mCT for both of them individually, and then you sum them up. That's how you can find the heat of the reaction. And then can you also calculate the molar heat of the reaction of benzoic acid? Try it yourself, pause the video, and I'll give you the answers shortly. This is the answer.